recall. I'm very pleased that Saad suggested we make this joint presentation on ozone optimization and how it can affect both sustainability and economics. From my days as a process engineer, I've always found that you have to look at a system in total, taking into account how optimizing the upstream and downstream processes affect each other when making changes to the various steps. And in an ozone system, here are the following benefits we will examine as they pertain to both sustainability and economics: conserving energy, providing a smaller footprint, decreasing chemical usage, reducing maintenance, improving downstream processes, and saving water. One of the most important areas where optimization can play a role is safety. And the Iowa Municipal Committee has done an excellent job in putting together this training video on oxygen and ozone safety. With that, I'll turn it over to Saad to discuss some of the case studies where ozone optimization has resulted in benefits to sustainability. Saad?
Okay, thank you, Jim. This work is about the process we had for the introduction of ozone for arsenic and manganese removal for the water treatment plant in White Rock, BC in Canada. Next slide, please. The city of White Rock received the water from groundwater, and which has a naturally occurring arsenic and manganese. And we see on the left-hand side of the slide, the level of arsenic, which is exceeding sometimes the level of the MAC or MCL for arsenic, which is 10 microgram per liter. The one on the right-hand side shows the manganese, which is exceeding the static objective, which is 50 microgram per liter, and reaching up to 200 microgram per liter, which is a big aesthetic issue. However, Health Canada introduced in 2019 a new guideline, which include an MAC or known as MCL in the United States. This one is about 120 microgram per liter and reduced the aesthetic objective to 20. Next slide, please. So the city of White Rock decided to introduce a new treatment plant, which they didn't have. They used to have the water supplied directly from the wells to the public. So the process we started by doing a pilot study, followed by design built for the water treatment plant, which is started in March of 2019. Next slide, please. The new approach which we used in the design for the plant is to introduce ozone for the oxidation of arsenic and manganese, which was based on the findings we had in the pilot study. And we continued to work in order to improve the quality of work and get an optimum applied ozone dose. Next slide, please. And this diagram shows the level of arsenic 3 and arsenic 5. Arsenic 3 is more carcinogen compared to arsenic 5. And arsenic 5 is the most dominant usually, which is you see it in the blue columns. And the orange columns is arsenic 3, which is known as arsenite. When we did the pilot study, we found that 0.5 milligram per liter was able to oxidize arsenic 3. However, because of limited time, we could not proceed into much lower levels. So the plant was designed for the ozone at 0.5 or up to 1 milligram per liter. But when we start operating, we start to look at potential improvement and introducing of a lower concentration of ozone to meet the objectives, which is the full oxidation of arsenic 3 to arsenic 5. And we see here when we went down to 0.4 and then 2.2 milligram per liter, we found that we are able to oxidize arsenic 3 continuously at 0.2 milligram per liter. Next slide, please. That achievement of reducing the proposed ozone dose from 0.5 to 1 milligram per liter down to 0.2 milligram per liter results in a reduction of capital cost if anyone wants to build a plant for the same purpose. So you reduce the capital cost to buy the ozone system and also reduce the operational cost because you're producing ozone at less than half the concentration we originally were planning to do. Also, there is a key issue here is the reduction of the plant footprint and because of the size of this application and additional processes we looked at. The reduction of energy was a key for operation of the ozone system. And the main thing in meeting all these issues is we still meet the design objectives for the water treatment. The next slide, please. One of the significant approaches is to reduce the footprint by, instead of building a contactor, and which will take a fair space, we introduced the use of the contactor of a pipe, a 600 millimeter stainless steel pipe, with the use of injector. Mazzei injectors were used here, which introduce the ozone directly into the pipe. And having the flow in the pipe as a plug flow, you get the best optimal contact time in plug flow operation. So we reduce the need to use a higher ozone dose, and that reduced the footprint systematically because we added this pipe we put it in the ceiling of the plant. So we save a lot of space. Next slide, please. The other things with the use of the side stream injection and mixing, the reduction, of the amount of ozone used, because there will be less ozone used and less of gas used into that. The Venturi injector produce a lot of fine bubbles into the pipe, which is reduce the waste of ozone into an off gas, and the result is a higher mass transfer rate, with an optimum ozone contact time. Next one, please. So in optimizing technology, ozone as a pre-oxidant was a unique approach into the application because the industry were used to use chlorine, the manufacturer for the filter media for manganese and arsenic removal. They were used to chlorine, and the use of arsenic, use of ozone, they were not familiar with it, and that's a unique approach when you see the quality of water produced. Next one, please. The bonus of small by reduction of the number of trees being removed. We have a high density of trees in the area. We removed only 38 trees for the whole size of the plant. And this will have an impact on climate change because it will capture and store the carbon dioxide, lower energy need for heating and cooling for the building. Next slide, please. The other experience we had was also on the application of ozone for the city of Windsor at the AH Weeks plant. This is back in 2001. Next one, please. And the water is filtered, was coming from the Detroit River, and longer filter runtime was achieved, improvement of particle count, the lower particle count, lower filter turbidity was achieved, and also reducing of chemical use. with the use of ozone. Next one, please. Cryptosporidium oocysts were detected in the intake, so we needed to look at a system to deal with it, which is ozone, and the use of particle counting enhanced the knowledge that ozone is improving the water quality by removing particles, which we use a system, a simulated size to the Giardia and Cryptosporidium. Powder activated carbon was used in summertime for taste and odor. That was eliminated, and that was a major cost. Ozone added a multi-barrier system for a safe drinking water to the public. So the improvement process include the performance and operation. And so ozone dosage were controlled, and we introduced a better way for the disinfection by the inclusion of the additional sections of the treatment process. We decrease the power needed for ozone generator, and the filter runtime increased in a very dramatic way, reducing the length of the backwash cycle and reduced backwash pump use, so reducing energy. So we did not see an energy spike because of the use of ozone. Filtered water was less used for backwashing when you have a longer filter runtime. In fact, filter runtime was increased from maximum of 48 to a maximum of 72 hours. And reduction of total annual cost when we did the calculation was $247,964.
Thanks, Saad.
Thank you.
So on the CapEx side, ozone optimization leads to a smaller footprint in terms of space and civil works. And on the OpEx side, ozone optimization results in reduced energy, chemicals, maintenance, and downtime. One of the ways to optimize an ozone system is to look at how to transfer the ozone into the water more efficiently. These methods should be evaluated on the cost criteria from the previous slide. So if you look at the different ozone dissolution methods, there's the fine bubble diffusers, there's side stream injection with basin nozzle manifolds, and then there's side stream injection using a pipeline that Saad just showed for his one case study. Ozone can create bromate in water that contains bromine, but can be mitigated when choosing the right ozone dissolution system, as shown in this Water Research Foundation report done a number of years ago. Here's a comparison between fine bubble diffusers versus side stream injection in terms of the time it takes to get for gas contact. And reduction in chemical use results in much lower cost than just the price of the chemicals in terms of transportation, inventory, product loss, handling, safety, downtime, disposal, and liability. And ease of maintenance with side stream injection gives the following benefits. Since it's hydraulically powered, there's no moving parts. There's minimal elastomers or polymers. Typically, the components are all 3/16 stainless steel. There's reduced downtime, and there's no confined space entry. And in one case study, this has shown significant cost savings. Maintenance costs for fine bubble diffusers versus side stream injection was higher by 27%. The estimated 20-year additional maintenance cost for fine bubble diffusers was $600,000. The lower mass transfer efficiency resulted in higher LOX use and power for the generator, and confined space entry for fine bubble diffuser was eliminated with side stream injection. Uniformity of mixing provides lower coefficient of variation. And this leads to the overall performance of the system being optimized. due to less hysteresis, thus improving the performance of all the individual components within the process. Thank you very much. And with that, we'll be happy to take any questions.